Now, what I've done is, with these numbers, if I multiply any pair of these numbers, that then in turn will tell me what the correlation is between those values. So for example, the value 0.854 times 0.866 and change gives me 0.74. And that should be my correlation matrix. This is what we would actually call sigma hat. This is or more specifically, this is the model implied correlation matrix and that's using the parameter estimates from the model. Now what I can do is I can compare this now. I'll actually move these numbers over. I can now actually compare these numbers to S. Make sure I've got this right. This is S, which is the sample correlation matrix for the actual items. Okay. So the question then becomes this: 662 and 685. The question is, are these good estimates? I notice that some of them are definitely much closer than others. So look at the correlation between Q3 and Q10. My model estimates it at 0.796. The actual correlation from the data is 0.795 with round. That's pretty close.
Where did you get the sample correlation matrix? Which output?
This one. Yeah. So if I go back to Stata, so inside of Stata, the command to generate it is just the correlation, Q13, and
that's what I'm looking at. I don't see those numbers matching up.
662, 715.
Okay.
Did I not grab the right 662?
No, you did. Sorry.
Yep. Now, if you do comma space C, that's the covariance matrix. So I don't want that one. Okay, I technically do want that one, but it's easier to do this analysis with the correlation matrix. But the covariance matrix is what State is actually using.
And now you're looking at, and above it is the standardized SEM coefficient.
Yep. These are the coefficients here. Yep. Okay. And the only reason why I put them on this column is it makes it easier for me to generate this. Because then I'd actually have ones going all the way down the correlation matrix. All right, so the key right now is the distinction between sigma hat and S. Okay, technically, I need to say this because, God forbid, this recording ends up in the wrong person's hands. Technically, this is sigma hat star and S star. All right, because it's easier to do this sort of go up one path and back down the other path to get the calculations. Because what I really need to look at technically is I need to look at the covariance matrix. So here's the covariance matrix. This technically is sigma hat. Okay? This is the model implied correlation. This is the covariance matrix. Sigma hat is the covariance matrix. Now, why is this important? Oh, no, I'm sorry. Sorry. No, this is S. This is S proper, what I've got here. This is the sample covariance matrix. My bad. Sample covariance matrix. All right. What I don't have is the model implied matrix. I actually don't have my sigma hat. All right. Now, in SEM, I don't have my sigma hat, but I can get, using eStat, I can do eStat residuals, and this will tell me how far off my values actually were. Okay, so this tells me how far off my values were. So if I were to actually come here and cut this, so I'm going to copy this into Excel. Again, it's a fixed width matrix. Now this is So this tells me how incorrect my values are. This tells me how incorrect my values are. I've got zeros for all of my diagonals because my variances are calculated pretty much without any problem. But as residuals go, these residuals are sigma hat minus S. So if I want sigma hat, I need to take the value from here and add it. So if I take this value and add it to this value, that will actually give me the corresponding sigma hat covariance for item Q1 and Q2. So my value is 0.94 and change, 0.943. The estimated covariance is off a little bit. Okay, so far so good. Now I'm going to show you something. Let's rerun our SEM this time, but let's get rid of Q10 and Q14 because I want to show you what happens if you only have 3 values. So if I run my SEM with only 3 values, okay, now I'm going to look at E-stat residuals. Look at my residuals. They're all zeros, aren't they? All right, so let's look at something. So I'm going to do, let me do this. Let me do SEM comma standardized. This will give me the standardized values. And I'm going to keep track of these 3 values. I want to keep track of 0.7991. I'll put it over here for now. I keep track of 0.833 and change and 0.90 and change. So those are my standardized values. Okay. Now I want to look at the correlation of Q1 through Q3. All right, so here's my correlation matrix. So I'm going to take my correlation matrix as well, bring it over here. Here's my correlation matrix. Try again. Copy. There we go. All right, let's look at my values now. Whoa, whoa, whoa. 7563, 7563. They're actually identical. 7151, 7151. Again, identical. 66, okay, with rounding 662, 662. It turns out that with just 3 values, I end up with a perfect fit. I was able to reproduce the model estimate for my correlation matrix happens to exactly equal the correlation matrix for my sample data. That's actually not coincidence. That comes from the fact that if we actually tried to write out the model and the estimates that we did the last couple days, it turns out I've got 3 unknowns and 3 equations, and I can solve them all quite easily. And they all work out quite nicely. So what we're seeing here is this is all good and fine. The only problem is I've got 3 measures. I have no way to determine if my parameter estimates are good because my parameter estimates were so restrictive that they only would work. These are the only values that could work, and I've got a single answer.
Can you phrase that in a different way?
I have 3. I want to ask the regression. It's sort of like just be getting lucky and finding the regression with points that all fall on the same line. Well, that's not a good analogy. That's actually not a good analogy because we would say in that case there is really good fit. What we ended up with is a situation where I had, in the first 2 examples from the last couple classes, the first 2 examples we were able to calculate our parameters perfectly. But in the third example, we actually ended up with an equation that with one set of values wanted one answer, and with another set of values wanted a different answer. So we ended up with an equation yesterday. I think it was technically gamma lambda. Or, I'm sorry, gamma psi. And one value wanted to equal 2, and another equation was supposed to equal 1.75. Well, the key is there's no way to make both of those work. The scenario we have right now with only 3 parameters is that we have 3 pieces of information that we want to know, and we have 3 equations that we can plug them into. Everything else is those. Because of that, we're able to get exact parameter values that will give us this correlation matrix back without any error.
How do you know we have 3 equations? I seem to be missing that, because if we had 4 variables, why wouldn't we have 4 equations?
We would. Well, actually, technically with 4 variables, we'd actually have 6 equations. The equations come from the number of distinct elements in the covariance matrix. So if we had 3 variables, we have a total of 3 distinct correlations or covariances. If we had 4 variables, we'd actually add 3 more. So that's why we've got 6. So it actually follows the pattern n times n minus 1 all divided by 2. That may have come up before if you've seen some of the stuff. That's what that's referring to. It's the number of unique values in the correlation matrix. Now again, I haven't really clarified this yet in any of the discussions we've had so far, but we're heading toward that. Okay. All right, so what I'd like to do now before we go and do much other changing, I'd like to now look at a 2-factor model. Okay, we'll look at the 2-factor model. We'll do a couple calculations really quickly once we've got it. And so let's see what we've got. So what I'd like to do now is, let me scroll down a little bit here. All right, so I'm going to do SEM, attentiveness. I'm actually going to do the following just because I kind of know what I want to happen here. I'm going to do attentiveness is Q1, Q3, Q10, and Q14. So in other words, I actually just got rid of Q2. Okay? It's also going to keep our data a little smaller. And for sociability, SOC is going to be, I think I've got my, sorry, let me double check it. Where are my things supposed to go?